Okay, so we teach physics in an interesting way, and basically we teach physics from a historical perspective, which is kind of an odd way to start looking at concepts. But as a friend of mine once said, that he went to look at the Feynman lectures, and if anybody remembers Feynman, Feynman was a Nobel Prize winning physicist and did a lot of lectures in physics and things like that. And he said, well, unfortunately, we've tried to figure out different ways to teach physics, and this seems to be the best. So what we're getting ready to do is electrostatics. And so this is a little bit different than how we approached Physics 1. Physics 1 was about mechanics, and we dealt with mechanic systems like how does, things in motion. We looked at things in motion. The big folks that we refer to in the West are Galileo Galilei. He was one of the first ones that said, yeah, we can measure and that there's a force called gravity, and there's a lot of those things associated with it. Then we get to Newton. Newton actually refines things and gets things going. And somewhere along the line, people start looking at electrostatics. And electrostatics goes way back, and we're going to take it from Western culture point of view because we don't have a lot of what happened in China or in the Middle East about it. We go through and we teach it from a Greek-based function. And what happened was, way back when, they noticed a phenomenon. I could take a rod of certain types of material and I could rub that rod with rabbit fur or something along those lines. And we noticed that you could actually pick up some stuff. So I can actually demonstrate that here. I can use a piece of paper. I'm going to actually do what my daughter calls them rippy bits. Okay, I can do some rippy bits here. I can get little pieces of paper. If you have a pit or a paper punch, you got pinhole or the hole punch, you get that. And I've got a piece of rabbit fur, but this time of year, we're really lucky because this time of year, it's the air typically is dry and we get to do this. And I can take my pin here and I can rub my pin. I'm going to rub my pin with my rabbit fur. And here's my rabbit fur. And if I rub my pin on my rabbit fur, we can actually see the rabbit fur start to move. I can see an attraction and make my little pieces of paper dance that we can actually get this. So we know that we've got some sort of charge on our pin. Now we call it charge because that's how we refer to it now. But I have that available to me. But we noticed that there was some sort of formal interaction. And we call that charge. So back in mechanics, we talked about fundamental units. And we said that in physics, we did things that had length, mass, time. And I don't know if you guys have been following things on the news, but time is a very interesting piece because mass and length are out there and time is this very different thing. And we talk about an arrow of time and we're not quite sure we measure it all the time. And that's that pun intended. We do a lot of things to measure that, but time is a real interesting concept. So we call that a fundamental unit. And now we're going to call another fundamental unit and we're calling it charge. Okay. And charge is our electrostatic piece. So we know that we have charge. Now, if you've taken chemistry, we talk about my atom, and my atom has a positive charge in the nucleus, and we have our electrons that are out there with a negative charge, and we have those pieces that are there, but we get that charge that's in here. My positive charges are around, and my electrons are out there. And then we did the Millikan experiment, and we know that my electron is a quantized number. It's going to have a specific charge, and we actually could measure that, and it's 1.609 times 10 to the minus 9 coulombs, I think. Hang on, I've got to double check something. It's been that kind of a day. I don't have all my notes, and I don't want to give you a bad number, so I'm going to go up here and I'm going to double check my charges. Nope, I was right. I knew I did something wrong. There's another constant that has an 09, and it's to the 19th. So the charge on an electron is 1.602 times 10 to the minus 19 coulombs. That's my charge on an electron. And my mass of an electron, just so that we have it, because we're going to use it. My mass of an electron is 9.11 times 10 to the minus 31 kilograms. Charge on a proton, it's the same charge, but it's positive. So we use a negative charge for an electron. We use a positive charge on a proton. But my mass of a proton, which is approximately equal to the mass of a neutron, although a neutron is has a little bit more mass. My proton is 1.67 times 10 to the minus 27 kilograms. So my proton is significantly, has more mass than my electron, but my electron and my protons have the same charge. My neutron's charge, just to remind everybody, is 0. It's a neutral charge. So my protons and my electrons are same masses or same charges, different masses, and my mass or my charge on a neutron is 0. But this is said to be quantized, and we actually did the experiment to show that the electron is quantized. So back in mechanics world, back in physics 1 mechanics world, we looked at mass, we looked at our distance, and we looked at the force that we had. And the force we talked was related to gravity, or we looked at the force due to a push or a pull. Now, this gravity force was a little different than my push or pull. My push or pull, we went back and we used the nominal version of Newton's second law, and that related back to our push or our pull. But if we dealt with gravity, gravity was different. we looked at, I had this big mass, and this was the mass of the Earth, and we had our little ball here, and we knew that the ball was attracted to the mass of the Earth, and it was a center seeking, right? It went to the center of the Earth, and this would fall, and we actually could write a force towards the center of the Earth. And we dealt this as the force due to gravity. And we could call this a field force. All right, we could call that a field force. So what's happening now in electrostatics is we're going to kind of look at the same thing. We're going to look at the world a little bit differently. Now, I will also tell you that for some people, electrostatics makes more sense than mechanics. For some people, mechanics makes more sense than electrostatics. But we can use parallelism between the two to help us out. So what happens here is we can look at my object, and just like what I just demonstrated, I could say that I have a positive charge here. And we could actually bring it into our little pieces of paper, and we could get the pieces of paper to move. Now, if my paper was a positive charge, what's going to happen to my paper is it's going to move away from. As I move this towards the positive charge, it's going to move away. So if I have two positive charges, the force that's going to happen is that they're going to move away. If I had two negative charges, they also move away. But if I have a positive and a negative charge, they're going to move towards each other. So what we say is that like oppose and opposites attract. Now, we've dealt with this and we play with that. With electrostatics, it's a little harder to see, but we've seen the same thing with magnets. If I have a magnet and I have two north poles that are together, we know that those two things are going to oppose each other. They're going to repel each other. I can take two north ends of a magnet and I can try and push them together, and they're going to do weirdness, right? They're going to, you can even feel that force between the two magnets as we're doing it. But if I do a north and a south, we know those are going to attract. Those are actually going to come together. And in some cases, if I have two magnets and I'm lightly holding them, one's going to jump to the other magnet. So we've dealt with this before in terms of magnets, but we've also dealt with it in terms of electrons, but we haven't really talked about it. It's not something that we really talk about or see, and we get those in there. So there's a lot of things that we can demonstrate to show this behavior. One common way is we've done the balloon thing. We take a balloon, we get it all charged up, and I'm going to say it's positively charged. And I bring that balloon to the wall, and all of a sudden it sticks on the wall. Well, why? Well, what happens is that all the little atoms in the wall are going to attract the negative to the wall, and then we're going to get what we call an induced charge. The negatives, as I bring this positively charged thing to the wall, all the negatives get attracted to the wall, and all the positives are going to go over this way. Okay? All the positives are going to go over that way. And for those of you who are in biology and we talk about hydrophobic, or we talk about hydrophilic. And we're dealing with a membrane. So if I have a little piece of cell, that is my representation of a long chain molecule. And one end is hydrophobic. We'll say the positive end is hydrophobic, and this end is hydrophilic. What's going to happen is if I have water on this side, all my little molecules are going to line up to actually give me a membrane that makes it attracted, and I actually get that membrane. It's because this is the water attracted side, this is the water repulsive side, and we're going to move that over. Similarly here, what happens is if I bring my positive charge to the wall, my negative charges are going to line up, and I'm going to bring that over. We see that with water all the time. Remember, my water molecule has two hydrogens and an oxygen, and my hydrogen ends are positive and my oxygen end is negative, and I get something that we call a dipole. And we see that in organic chemistry. We see that all over the place where I'll all get positives and negatives. My charge carrier here, what's free to move are my electrons, which is a little different because we're going to all hate Ben Franklin. Because Ben Franklin actually had the opportunity to pick which things, as we are dealing with electricity, which things that happen, and we deal with that, he picked the wrong one. So things are going to be a little backwards because Ben Franklin picked the wrong one. We now know that it's the electron that's mobile, and it can move around. Right? It can move around. It's what's actually going to be our charge carrier in a wire. It's going to be my electron. My electron is the thing that can move in my hydrophilic and my hydrophobic big molecules. It's my electrons that move. It's my electrons that move in my water molecule. This is going to be hydrogen. I'm going to go ahead and make this easy so you guys can see it in your notes. This is my water molecule. And we know that we've got a negative charge, and we got positive charge, which gives us our dipole, and we get those things that are in here. So as we get into electrostatics, we're starting to talk about field forces. And we saw field forces in mechanics, but it was just a little different. We dealt with that primarily when we were dealing with gravitational. But remember, we also dealt with, on the mechanics side, we had this. We had the force was equal to G M1 M2 over R squared, and the force was in the R direction, which gave me, if I have this being the Earth and the moon here, these forces were attractive along the R direction. And this is Newton's law of universal gravity. And that gives us a field force. And I could draw that field force if I'm right here at the surface of the Earth. I used lines like this to represent my field. So we can actually use those arrows to represent the field, and the directions of the arrows is what's going to give me the primary force. I'm going to get these field forces. Now, back here, when we were talking about an induced charge, like bringing my positive over to my negatives, I got that induced charge. We can also charge by conducting, and this is when we touch. This requires touching. So in this case, if I have that, let's say I'm going to go ahead and give myself a lightning rod. We can have the lightning rod come in and we have it connected to the ground, and this would be considered a ground. And I'm going to put this as a lightning rod. And the electricity that gets generated in my lightning rod due to induction or due to something else is going to be conducted through the ground wire to the ground. And why is that important? For a lightning rod, it's very important because if I have a big cloud that's all charged up with negative and it comes in, we get that traditional zot. And if I don't have a way to take that electricity from the zot into the ground, I may have a lot of damage in my house. Or that zot, if I'm at the gas station, that zot might be enough to trigger an ignition of gasoline vapors. So we have to really worry about how we're doing that. And that's one of the reasons that they say to ground yourself before you fill up your gas tank, because you don't want to create a spark. And the spark is our zot. That spark, we don't want to create a spark that might ignite our gasoline vapors. And we know we can ground ourselves this time of year. Probably as you were at home and the house was heating up as it got really, really cold, the house gets really dry and we get really dry air. And if you were wearing little socks and you went over to a metal doorknob and you got a zap, right? You absolutely got a zap as you connected. There was a spark of electricity that jumped from you to the doorknob and you created that electricity. So we end up with that. But on the mechanic side, we have this force. Now, we also can demonstrate, like I said, we can demonstrate a lot of different things. We can demonstrate that opposites attract. There's a gizmo, and we have a metal ball, and we have a metal ball, and it comes down here, and hanging off of this are two pieces of some kind of conductive metal, be it aluminum, be it gold, be it something like that. We get our charged rod. Okay, we get our charged rod, and I'm going to say it's positive here. And we bring that over to this and we touch it so that this now all becomes positive. And these become positive. And if these are positive, they're actually going to move away from each other. And you can actually see that. You can take a little piece of aluminum foil, take a plastic pin, get it charged up, hang it over and do this little thing right there, and you can get it to stand apart. We see that all the time. Now, we all know that I don't do stick people. I don't do people very well. So here I got my person that's smiling, and as they charge up, what happens to their hair? Their hair all starts to stand on end because now the hair's all positively charged and each hair wants to move away from each other, and we're going to get our hair to start standing on edge. And if you're ever in a thunderstorm and you feel like the hair on your arms or the hair on your head starts doing that, these are all going to want to move away from each other to balance each other out, and that's what's going to cause that hair standing on your head. When we get there, which will be a little later in the semester, because we still want to do a couple more experiments related to sound, we'll do an electrostatic observation experiment in the lab, and you're going to go out and you're going to look for evidence of electrostatics. So just be aware of that. So the hair standing on your head, taking a balloon next to your hair and seeing it rub, doing exactly what I just did with my rabbit fur, getting my rabbit fur and moving my rabbit fur with the pin, because the pin is all charged up. These are all evidence of electrostatic. It's also fun to play with styrofoam cups, styrofoam plates. There's a lot of things that we can do that actually demonstrate this. Now, Coulomb, which is what we talk about for our charge, and our charge is good old Coulomb. We use that unit. Coulomb showed that there was a relationship. So as I take the rod and I have a little, what we call a pith ball, and this pith ball is coated with some sort of dust that's electrically conductive. Remember, we have conductors and we have insulators, all right? Insulators are not going to carry electricity. Conductors do carry electricity, but I could have an insulator. So if this is hanging on a string and this is positively charged and that's positively charged, as I approached this would start to move, and he just saw that the magnitude of my force was proportional to the distance over r squared. Interesting. You see the same thing with gravity. It's there. He also showed that the magnitude of the force was proportional to the charge on one object times the charge on two objects. So the relationship between these two objects, whatever my charge is, and we're going to use the letter Q, whatever this charge was, whatever the magnitude of that charge was, my force was proportional. And then he showed that the force was proportional to Q1, Q2 over r squared. And in order to make this work, the force, and this is the magnitude of the force, was equal to something that looked like this. Very much the same form as we see with Newton's law of gravitation. Exactly the same form, except we've got a different constant. And I'm going to be good, and I'm going to look up the constant first. I'm going to actually look up both constants so we have it. I'm going to write down the information that we need. So these are some pieces of information that we need. Okay. We need gravitational constant. We need our Coulomb's constant. We want the mass of the electron. We want the mass of the proton. And we want to know our charge of an electron or proton. And we've already looked up a couple of those. Okay, my charge is going to be 1.602 times 10 to the minus 19 coulombs. My mass of my electron is 9.11 times 10 to the minus 31 kilograms. Mass of my proton was 1.67 times 10 to the minus 27 kilograms. Okay, I want Coulomb's constant. Coulomb's constant is 8.99 times 10 to the 9th, and it's Newton meters squared coulombs squared. A lot of times we're just going to use 9 times 10 to the 9th. Okay. I'm going to use that value a lot because it's easier as we are working our sample problems and we're doing things that we're able to deal with that. I'm going to look at my gravitational constant here. My gravitational constant is 6.67 times 10 to the minus 11, and it's in Newton meters squared kilograms squared. All right. So, I wanted one more piece of data. Need one more piece of data. Okay. All right. I need a Bohr radius. Okay, a Bohr radius, because we're going to do this. Bohr radius is a radius of length, and it's 5.292 times 10 to the minus 11 meters. Okay, 5.292 times 10 to the minus 11 meters. That's a Bohr radius. Because what we're going to look at is we're going to look at a hydrogen atom. And we're going to compare our electrostatic versus gravitational force. Okay, we're going to compare the electrostatic and gravitational force in a hydrogen atom. Hydrogen atom consists of a proton and an electron, and the Bohr radius is the distance between our proton and an electron for the first ground state of our hydrogen atom. So it's going to be a Bohr radius, which is why I wanted to look up the Bohr radius. So the gravitational force for my atom, and we're just going to look at the magnitude here. We're not looking at direction yet. We're just looking at the magnitude. It's going to be G mass 1, mass 2 over the distance squared. So I'm going to get G over the distance squared, and I'm going to have my mass of my electron and my mass of the proton. So if we do this, I get my 6.67 times 10 to the minus 11 divided by 5.292 times 10 to the minus 11 squared. And I have my 9.11 times 10 to the minus 31 kilograms. And I have my 1.67 times 10 to the minus 27 kilograms. I'm going to go ahead and square this number because I want to show you something else. 5.9. Okay, one of the things I do want to show you on your calculator, depending on which calculator you have, how you're going to enter exponents, because we're going to be dealing with a lot of exponents and we want to make sure that we're handling them right. So on this calculator, it's 5.292, and I do an e to the minus 11. Now, I'm going to go ahead and hit enter. So my calculator has the number in appropriately, and then I'm going to square it. And if I square that, it now gives me that this number, I'm going to do 6.67 times 10 to the minus 11 And then I have 9.11 times 10 to the minus 31. And I have 1.67 times 10 to the minus 27 divided by 2.8 times 10 to the minus 21. If you have one of the other calculators, this is where life is going to get a little entertaining. Sorry, Robert, didn't realize that you had popped off and I just saw you back in. So I apologize for not catching it sooner. So we end up with, look at all of these lovely exponents. So as a reminder, and I think I reminded you all about this when we were doing and starting to deal with decibels, in Appendix A of your book, it does show you how to deal with your exponents. So I'm going to go ahead and write this out, and we're going to play with it just a little bit because I want you all to be very careful about your exponents and about how you enter it into your calculator. Because depending on your calculator, the order of operations sometimes becomes a problem, and you'll punch in the numbers and you think you've punched in the numbers correctly, and you find out that your calculator is handling the exponent a little differently. So if I'm using my exponents, and if I'm multiplying 10 to the A times 10 to the B, this is going to equal 10 to the A plus B. If I'm doing 10 to the A divided by 10 to the B, this gives me my exponents of A minus B. So up here, I'm going to get a number of 6.67, 9.11, 1.67 divided by 2.8, but I have 10 to the minus 11. I have 10 to the minus 31. I have 10 to the minus 27. And I have 10 to the minus 21. So if I do this, I get minus 11, minus 31, minus 27, minus a minus 21. Now I get something that's a little easier to play with. I'm going to end up with minus 48. So I'm going to end up with 10 to the minus 48. Now I can plug these numbers into my calculator real easily, and I don't have to worry about whether or not my calculator is going to handle the exponents correctly, because I've already done that for it. And I get a number 36.2 times 10 to the minus 48. And this is in newtons, because let's look at my unit analysis. My G has units of Newton meters squared, kilograms squared. This was in kilograms, this was in kilograms, and this was in meters squared. So that cancels out, that cancels out. I'm in newtons, and so I have a force. So this is the gravitational force between one electron and one proton in my hydrogen atom. Now we're going to calculate the electrostatic force. And my electrostatic force was F K Q Q over R squared. So I'm going to get my K over R squared. And I'm going to get my charge of my electron, my charge of my proton. We're dealing with magnitude here, so I don't have to worry about the positives and negatives. I'm just doing the magnitude of the charge. I'm going to get my 9 times 10 to the 9th. I'm going to end up with my Bohr radius, which was 2.5 times 10 to the minus 21 meters squared, because I did that for the other one. The R squared is the same. I've got my 1.602 times 10 to the minus 19 squared, because that magnitude of that charge and the magnitude of that charge is exactly the same. And if I go ahead and square that, I get 9 times 10 to the 9th, 2.8 times 10 to the minus 21. And this was in Newton meters squared, Coulomb squared. This is in Coulomb squared. Coulomb squareds cancel, meter squared cancel. I'm going to be in newtons. And if I do this, I get 2.566 times 10 to the minus 38. And I get my 10 to the 9, my 10 to the minus 38, my 10 to the minus 21. I get 9 plus a negative 38 minus a minus 21. This is going to give me ten to the minus 8. And now I'm going to do my 9 times my 2.566 divided by my 2.8. And I'm going to end up with 8.25 times 10 to the minus 8. And this is newtons. And this is the electrostatic force between my proton and my electron in a hydrogen atom. Note that that's 10 to the minus 8. This is 10 to the minus 48. This is huge in comparison to my gravitational force. So when we're dealing in our chemistry and looking at ionic bonds, you can see that that electrostatic force in my ionic bonds is huge. And we don't even have to worry about the gravitational force because it's so small in comparison to the electrostatic force. I only have to deal with it. Don't even have to deal with it. Don't have to mess with it. It works really, really well for me. So it becomes very, very important to work with that. All right, let's look at the forces between particles. So we're going to look at, because we do have something different, the difference between our gravitational and our electrostatics is this case, everything was attractive. We only dealt with stuff that was attractive. And in this case, we have both attractive and repulsive forces. We have attractive and repulsive forces. So we dealt with that all the way around. So now, if I look at our positive and our negative charge of our hydrogen atom, and we want to know the direction, well, the direction is between these 2 points. Because when we did the problem, we just looked at the magnitude. But in this case, the direction is between those 2 points. But what happens if I have 3 particles? I have a positive, I have a negative, and I have a positive. And I want to look at the force on this particle. Well, the particle is going to want to travel in that direction because that's positive. It's also going to want to travel in this direction because it's positive. But which force is going to win out? What direction is that particle going to actually travel? Because we don't know these charges. We don't know that charge. And we don't, if the particle traveled this way, we know that this charge was bigger than this charge because I actually drew this as this being the same distance. So we could intuitively look at if this was 4 charge, and this is 1 charge, and this is 2 charge, we know that this object is going to move in that direction because the 4 charge is greater than the 2 charge. So we can look at a system like this and figure this out. So let's do one of those. So we're gonna take some distances here. I'm gonna do this right here. And I'm gonna say that this has 3 times 10 to the minus 3 coulombs. It's gonna be separated by a distance of, we're gonna say 0.5 meters. This is gonna be a -1. And this is going to be 5 times 10 to the minus 3 coulombs. And now we're going to put this one right here. And this is going to be 0.75 meters. And this is going to be, we'll make it 6 times 10 to the minus 3 coulombs. And we're going to say that's negative. We want to know the force on this charge. We want to know the force on that charge. All right, let's look at this because we're looking at from this charge's perspective. This charge is going to want to move in that direction based off of this one. So this is the force related to my 3. This one is also going to want to move away from that one. So this is the force due to the 6. So we know which direction this charge is going to move, but we don't know the forces. Now we've done these problems before. The force on my 5 charge is going to equal the force from the 3 charge plus the force from the 6 charge. We're adding up our forces. Now we're in 1 dimension here, so this is only going to be the direction that we're going to get is left or right. And we already know which way that's going to go because we're looking at our diagram and we're going to say it's to the left. Okay? We're actually going to be able to tell that it's to the left because of the way we've got our picture. So now all I got to do is calculate the magnitude of these forces, and we know it's going to move to the left. So the force due to 3 is going to be K, my Q to the 3, my Q to the 5, divided by the distance between 3 and 5 squared. Well, this is 9 times 10 to the 9th, and that's Newton meters squared, coulombs squared. I have 3 times 10 to the minus 3 coulombs. I have 5 times 10 to the minus 3 coulombs. And it's all divided by 0.5 meters squared. So we're going to be in newtons. Okay. And if we've got our calculator and we've cleared our calculator and we know how to use it, I'm going to do my 9 times 3, here's 3, times 5 to the minus 3, divided by 0.5 squared. I get a number of 540,000 newtons. Or if I keep it in there, it's going to be 5.4 times 10 to the 5th. Hang on. 10 to the 5th newtons. That's the magnitude of the charge related to my 5 or my 3. Now I'm going to do the same thing for the 6. So this is going to be the 6th one. I get my 9 times 10 to the 9th. I get my 5 times 10 to the minus 3. I get my 6 times 10 to the minus 3. And I'm dealing with 0.75 meters squared. We know that's also going to end up in newtons. And that gives me 4.8 times 10 to the 5th newtons. And so my total force, come back up here to my total force, this was 5.4 times 10 to the 5th. This was 4.8 times 10 to the 5th. It's going to equal 10.2 times 10 to the 5th, or 1.02 times 10 to the 6th newtons. And remember, if I want to enter this number into WebAssign, this is how I would enter the number. Actually, I'll enter it like this: 1.02 e to the 6th. That's how I would enter it into WebAssign. Just a caution, okay? A total caution. You usually have 5 tries in WebAssign. As you guys are working your homework, if you get to 3 tries and you still haven't gotten the right answer, that's the time to do the Ask Your Instructor. And do it in WebAssign so I can come straight to that problem and be able to see where you're at and see if I can help you. I don't want you to be fighting, maybe using one of the calculators that's not doing the order of operations correctly, and I have to help you through that. But definitely get to know your calculator, because we were dealing with a lot of exponents here, and I don't want you to waste your time and your answers in order to figure out certain pieces. So be aware of that. Okay. I'm going to set up a problem. I don't really have time to do it today and not have everybody go totally stir crazy, but we can do charge configurations that are a little differently. I can have a charge at the origin. I'm going to make that a positive 5 and I'm going to say this is nanocoulombs. I'm going to do that for a reason. And that's a positive 5 nanocoulombs. This is a negative 3 nanocoulombs. And this is a positive 6 nanocoulombs. And we're going to say the distance here is 0.4 meters, and the distance here is 0.6 meters. We want to know the direction of this charge. First of all, we want to know the force on this charge. First of all, nanocoulombs is going to equal 10 to the minus 9 coulombs. Okay? Millicoulombs is equal to 10 to the minus 6 coulombs. Oops, 10 to the minus 3 coulombs, sorry. Microcoulombs is 10 to the minus 6. So this is 10 to the minus 3. Because we'll use these because our numbers are so big when we're dealing with our 10. Now, remember that if I'm doing these charges, I've got a positive charge here, I've got a negative charge here, and I got a positive charge here. What's going to happen here is this is going to be attracted. So I've got one vector that looks like this. This is going to be repelled, so I have another vector like this. My resultant vector is probably going to look something like this. I'm going to have to remember my vector addition. So depending on my magnitude of my red one, say it's a magnitude like that, and my blue magnitude is like this, we can add head to tail. I didn't do that very well. I meant for this to be my arrow here. My resultant vector is going to come out like this. Now, the way I have that set up, remember, if I do my resultant vectors, if I have vector A, and this is going to be AI, and my vector B is equal to BJ, my vector R, my resultant vector, is going to be my AI plus my BJ. Just remember your vector addition and you'll be in good shape. Okay, I'm going to leave it there. And I'll open our questions.